Okay. All right, I'm live. Okay, cool. And share the stream. Okay. Control C. Minimal mental. Okay, so we're just posting an announcement. Live stream for exam 1 review. Come watch. Okay. Oops. Okay. And let's try that. Okay, who gave me that cable this morning? Oh, you did. Can I give it back to you? Thank you so much. You saved my butt. That's great. And what did I do with it? Oh, hold on. There it is. Thank you. That was so awesome. Thank you. Okay. All right. So hopefully the live stream is good. We're good. We're live. We're live. You guys could see yourself if you want. Let me just log in. Okay. So our plan is we're going to start with chapter 4 and then work back. We'll do then roll back to chapter 1. We'll do the questions right after chapter 4 as well. Okay. So kind of lock in some of the new ideas that you got today. All right. So I just want to check to see if we're functioning here. For our people at home, if you're joining us at home, thank you for joining us at home. I promise that we will have a big reveal by the end of the show. One more frequent. Okay, here we go. Well, announcements. I got to do announcements. Okay, here we go. You should be able to see this. Okay, live stream for exam 1. Okay, and it should be working. Should be working. Hello? Hello? Okay, it's working. Okay, all right, that could be an endless feedback loop. Okay, so going to files, I'm going to just check on my study guides. And I'm going to grab the first study guide, okay? I'll download that. Okay, now I could work off of this, but I think I'm going to try to work off of the actual file. Oh, I had it right here already. Okay, well, that was before. Okay, so we are going to jump to the last chapter somehow. There we go, chapter 4. Okay. Okay. And we're going to look over these definitions. We're going to start with chapter 4, then roll back to chapter 1. Yeah. Go back to 3 after that? One more time? Can you? Yes, absolutely. It's recorded afterwards. The live stream is recorded. You can watch it later. Sure, absolutely. So if you miss anything when we're going over it fast, you can go back and watch it later. Okay, so let's try to go over these terms right here. These are words that you're supposed to recognize. So a spectrograph is the idea of the spectra, the light spectra. And we saw this today, particularly with the Blackbody spectra. There was a shape for the light that came out of a hot object, and the shape changed depending on what the temperature was. But there's not just a single color that comes out, it's a whole range of colors. That's what we mean by the spectrograph. Okay, so all of the colors that can come out of something, the spectra is another way to say that. But a spectrograph is a picture of the colors that come out of an object. So the way that we talk about it is usually with the frequency along the axis. Okay, so we could actually look at a picture if you'd like, a picture of a spectrograph. I'm going already off topic, but I guess it's useful. Spectra, just to remind you, right? What is a spectrograph? Okay, so this is the spectrograph, a picture of the colors that come out of something. Okay, spectrograph. So we actually learned today, or you're supposed to know that there are 3 different kinds of spectra, and we'll come back to that in a second. So before we do that, let's talk about the other words. Okay. Okay, so wavelength. Anybody got the wavelength? Okay, anybody define wavelength for me? A wave is a pattern that repeats itself, right? A pattern that repeats itself. The distance required to make one complete cycle is called the wavelength, right? What about frequency? There's a definition that you're supposed to know. The number of waves created per second or passing a given point per second. Number of waves per second. And in particular, remind yourself also, how do we measure that? How do you measure wavelength? What would it be measured in? It would be a distance, so it would be measured in meters. But frequency is measured in another unit we called hertz, right? So Hz is the frequency unit. Okay, the word amplitude, another word you're supposed to know, refers to what? The size of the wave, the size of the wave. And it's always measured from the middle to the top or from the middle to the bottom, right? It's from the middle, the center, the equilibrium. Do you guys know what that word means, equilibrium? Ooh, I think I might have to come back and make sure you know that word. It's a pretty important word. Electromagnetic radiation, what does it refer to? What does that mean? You should say light. That's light, okay? Whether it's visible light or invisible light. So electromagnetic radiation is the idea. It's a wave which is made of an electric and magnetic part. The electromagnetic spectrum is really the light, all the different colors of light, okay? The electromagnetic spectrum. So it comes in a bunch of different colors that we can see. Those are the visible colors, and then lots of colors, much, much more that we cannot see, invisible colors. So can anybody tell? We'll come back to that. Refraction. Again, I didn't talk about that, but we will talk about that tomorrow, just for briefly. But why do we say it today? Refraction is the word that says light bends when it passes from one material into another. When light passes from air, for example, into glass, it changes direction slightly, and that word is refraction. So this allows us to create a device called a lens. You might have heard of a lens, like a magnifying glass lens, or a telescope lens, like Galileo used. The principle is refraction, the bending of light that happens when you pass from one material, like air, into another, okay? Spectrum, I feel like it's pretty redundant. Spectrum, again, is a spectrograph would record the spectrum of something. Okay, I guess I'm kind of mixing up the words a little bit. But spectrum, all the different colors that would come out of an object. Actually, spectrograph is almost, I don't know. What's the difference? Spectrograph, maybe the device needed to take a spectrum, come to think of it. Okay. Kinetic energy, we talked about that today. Kinetic energy, the energy of an object which is moving, right? So anything that has mass and is moving has kinetic energy. And then another kind of energy is this thing called gravitational potential energy. And the way that you might think about it is any objects that attract each other with the force of gravity, when you pull them apart, they have potential energy. So I described it in a more simple way, right? If I take my keys, because I don't have whatever I dropped earlier, and I lift it up, right? As soon as I let it go, it begins to fall, right? It's attracted to what? Attracted to the Earth, actually. The force of gravity that you and I think about is really the attraction for this mass to the body that we call the Earth. We are attracted to, and that's what we call our weight. And so by lifting it up, I kind of give it some kind of energy, and that energy we call potential energy. If it drops, it begins to lose potential. It's getting closer to the Earth, right? But in the same moment, it's gaining speed. So what kind of energy does it gain as a result of gaining speed? Gains kinetic energy. And if you remember the words, there's a concept called conservation of energy. Is it up there? I don't see it. It should be. Probably a mistake. Energy cannot be created or destroyed, only transformed from one kind into another, okay? And now another kind of kinetic energy, but at the molecular or atomic level, is called thermal energy. And so air molecules are whizzing around really fast. That's kinetic energy. The thermal energy is basically kinetic energy for small things that we don't actually see very well. But it is, in fact, a kind of kinetic energy. So if I drop my keys, ready? Boom, right? What happened as they fell? They went faster. The potential was changed into kinetic. And then they landed on the floor. And now how much energy do they have? They don't have any energy. But wait a second. Did I just destroy the energy they just had? No. Believe it or not, the ground, the keys, and the air around them just got a little bit warmer. Okay? That energy is there somewhere. I just can't see it now, right? But it must be there. So it becomes a kind of thermal energy when you're done. Okay? So yeah, question?
It goes from potential energy.
So thermal is just kind of like when I can't keep track of it very well. I might say that it's thermal energy, but in fact, in other cases, like when we talk about how stars are made, we'll talk about like large amounts of material falling together. And the process of falling together automatically generates kinetic energy, which we will interpret as thermal energy. Okay, so, all right. Thermal energy. Oh, okay, I just talked about that. Thermal energy is the energy of hot bodies, right? So something that's warm has thermal energy. Blackbody radiation, we again learned about today, is the idea that everything that has a temperature is glowing with light, including you, right? And I should, did you guys look at your pictures yet? You can look at your pictures. You guys know I posted those, all those pictures I took, right? I think it's really cool. I want you to really think about that. And by the way, there's a question on your test tomorrow, right? So, you know, I'm trying to be relevant too, but it's kind of amazing to think that you're really glowing. You are glowing with light, okay? I think that's really awesome. I like that. Look, you see? So the resolution is not very high. That's okay. But you can see there's hot, which is reddish, and cool, which is green and blue, right? So, or kind of pink, I guess, it's a little bit. I don't know. I'm not sure about that. But you can see your faces are the hottest parts of your body, right? So, and maybe you can see your own face, right? So you can look through here and see your faces. Okay, there's Karen over there. Okay, so anyways, it's an important idea, and I think it's also neat to understand that the universe is full of light. Okay, everywhere you look, you can't see it, but there's light everywhere you look. Okay. Blackbody radiation, the light that comes out of a hot object, anything above absolute zero, which is basically everything. There's no such thing as absolute zero. Okay, so now jumping to the next word, photon. Anybody tell me what a photon is? Photon would be a particle of light, a little bit of light energy. And the relevant formula, even though you don't need to know the formula per se, there is a formula. The energy of a photon is probably the most important thing that we're going to need to know about, right? Photons are little bits of energy. How much energy is a question, right? And the answer is, let me go ahead and roll my projector over here so that our viewers at home can see this too. But the energy of a photon is h, some constant, times the frequency. It is directly proportional to the frequency. So the higher the frequency, the higher the energy of the photon. If you double the frequency, you double the energy. 10 times the frequency, 10 times the energy, right? Directly proportional. Pretty powerful idea. Okay, and our next term after photon. Wien's law is the location of that peak, the energy peak, the spectra. Where is it? And we learned today that it is inversely related, inversely proportional to the temperature. So if we ask ourselves, how about the sun? Okay, because you need to know this. Where is the peak wavelength for the sun? What color does the sun put out more than any other color? Green. Make sure you know that. Okay, if you wanted a number, it's 500 to 2 nanometers. Okay, I can go look that up, right? But it's a certain color. It's green. Okay. Now, what happens if you heat something up to hotter than the temperature of the surface of the sun? Where does the peak go? Higher temperature leads to the peak going which way? Towards higher or lower wavelength? Higher temperature makes the wavelength smaller, which means higher frequency. Do you remember what we looked at? Very, very hot stars are going to have their peak in what part of the electromagnetic spectrum? in the ultraviolet, right? So the peak is in the ultraviolet. How do the stars look because of that? They look kind of blue. They look blue to our eye. Now, if you get a really cool star, the peak is not going to be in the visible at all. It'll be below red. So what color will it be? Infrared, right? The peak means more light comes out at infrared than anything else. When we look at the color of that star, it's going to be red or orange in appearance because it puts out more orange and really much less violet and blue, okay? So the color of a star tells us about the temperature of the surface. This is a really important idea for later in the class, okay? All right, so that's Wien's law. You don't actually need to know the law, except what does it say? The position of the peak changes. The higher the temperature, the shorter the wavelength for the peak. You could try it the other way. The lower the temperature, what happens? The longer the wavelength will be for the peak. The peak wavelength, where is the peak? In other words, which color comes out more than any other color? All right, jumping up, Stefan-Boltzmann. Again, you don't need to know the whole law, but you need to know what pieces are important, right? When things are glowing with light, this law has a formula. Maybe I should write it down just because it has a formula that you need to know. You don't need to know the formula, sorry. You need to know the behavior. And the Stefan-Boltzmann equation said that the luminosity, so we'll have time to share with you a little bit more about this. The luminosity of a star has a constant. It's the Stefan-Boltzmann constant times A, and this one is important, A. A is the surface area. So the larger the star, the more area it has emitting light. And then the last term is temperature to the fourth power. So the temperature really matters a lot. It's kind of the most important factor for this, okay? So higher temperature means more light, but also larger star means more light. So you guys will be able to answer the question, you know, how much more light or less light, depending on how I change one of those things. So area, the last thing that I forgot to write down before I moved my computer, the area formula is 4 pi r squared. So what does it mean? Larger has more area, but if you double the size, you get 4 times the area. 4 times as much light will come out just by doubling the size. If you make it 5 times their size, how much light comes out? 25. This factor is getting squared. Okay, that's a behavior that we need to understand well. Okay, so we have the luminosity, is that equation right there, which is Stefan-Boltzmann. And, oh, new thing, nebula. Okay, so does anybody know what nebula means? Nebula? Glowing, yeah. Glowing stuff. Glowing gases actually is a nebula. Glowing gases. So we will see out in space that there's patches of space that are just glowing. They're not just glowing. They're glowing because something is pumping energy into them, and then they're glowing with light as a way to get rid of that energy. Okay? So we'll be studying that more in the class, but a nebula just means a glowing patch of gases in the universe. Okay, so here we go. This is going to be new for you guys because we haven't covered it before. The concept of quantum physics, quantum mechanics. Okay, this is actually like a multiple year course, and we're just learning a little tiny bit. Okay, so don't be intimidated. We're just trying to learn a little bit. But the number one idea of quantum physics is that energy comes in small pieces, like the concept of a photon. Energy comes in small pieces. The word for this, small pieces, is quantized. So the term for quantum physics is little bits of energy. And it's not just energy, it turns out, it's lots of other things as well. We don't have to worry about everything, just the energy part today. Okay, so energy comes in little pieces. We've learned about little bits of light energy. We call them photons. Okay, so the way that quantum physics comes about, quantum mechanics comes about, is when you study things that are very tiny. We don't normally see it in our everyday lives. It's not something that you and I will have to confront very often, unless you deal with really tiny things like atoms. An atom is an excellent example of a really tiny thing. So if you take an individual atom, you discover that it's quite remarkable. It's really amazing how atoms are going to function. So today we want to learn a couple of ideas, very, very quick and simple ideas about how atoms work. So you know that they have a core. Does anybody know the name of the core of an atom? Has a name. It's called the nucleus. And what would you find inside of the nucleus? Protons and these things called neutrons, okay? It turns out that the most important atom that we would ever want to talk about is the atom called hydrogen, and it happens to be the simplest atom. So what I want to do is talk to you guys about hydrogen very quickly here, hydrogen atom. Okay, so I'm going to draw a little diagram here. This is the nucleus, which is actually just one proton, one positively charged proton. And if you're an atom of hydrogen, you have one proton, but you also have one of these outside of it. What is that? The electron, one electron. Okay, so here we go. This is a strange idea. Now, I'm not going to tell you why this happens, because frankly, I don't know the answer to that. But we have observed something wonderful about electrons inside of a hydrogen atom. We have discovered that the electrons can be in these states around the atom. So the states of the electron. And these states are separated from one another. So we call this state right here, we call it level 1. We call them energy levels. That's another word. They're actually going to be associated with energy levels. Okay? And we call this first level, level 1. It has another name. It's called the ground state. Anybody want to guess why it's called the ground state? It's like the ground, right? Can you go any lower than the ground? No. And so it turns out this is the lowest energy state that the electron can be in. It's also the closest that the electron can be localized near the atom. So where we find electrons usually is right there. The electrons are typically found in the lowest possible level, the lowest possible state. But there are other states, okay? So you want to guess what the next level up is called? Next level up. How about 2? It's pretty easy, right? We got level 1, we got level 2. Anybody guess the next one? How about level 3? Okay. Am I getting boring? Okay. So I want you to notice something, that the levels are separated from one another. These are called discrete. That just means separated from one another. And what do you notice about the spacing between the levels? What's happening as you go higher? They're getting closer together, okay? So these are the key ideas that you need to understand, okay? So the electron is normally found here, but the beautiful thing is electrons can jump. Okay, have you seen that movie, Electrons Can Jump? No? Just kidding, okay. So how does the electron jump? That's really the idea. These are energy levels. So n equal 1 is the lowest energy level, right? This is the lowest energy level, closest to the nucleus. If you jump higher, did you get more or less energy? Do you have more or less energy? What do you think? Okay, I just told you it's lowest. So you can understand that level 2 is a higher energy level. Level 3 is higher than that, okay? So how do you go from level 1 to level 2? The answer is by gaining energy, okay? So we will learn a really amazing thing, that the electron has the capability of absorbing a photon. So if the right photon comes along, then the electron will absorb it. And what will happen when it absorbs it? It will gain that much energy. And so it can make the jump, right? So how do electrons jump higher? You can tell me the answer right now. By absorbing a photon. But be aware that this is actually a game, actually an app called Tinder. You heard about Tinder maybe? The electron is playing with this app right now. And I forgot, which way do you swipe if you like it? Who knows? Left or right? It doesn't matter. Left or right? I don't even know. Okay, whatever. The electron's like, most of the time, not interested. Nope, swipe, whatever. Okay, not interested, not interested. It's only exactly the right amount of energy that would make it jump to another level that can be accepted. It will only swipe, let's say right. It will only say, yes, I'm attracted to you, if that energy is just the right amount to get it to another level. The electron cannot be in between these levels. It can only be in the levels. Okay, so again, I'm not explaining why. You just have to believe me when we see that this is true. So the electrons will only absorb certain energy photons. So what did we learn today about the energy of a photon? It's related to what? The frequency of the photon. And the frequency of a photon is related to the color of the photon. So if you shoot in a whole bunch of photons with all different energies, the electron's going to ignore almost all of them. The only ones that it's interested in are the ones that take it from where it is to another energy state, another energy level. And so if you shoot in continuous light, which is all these different colors of light, what will the electron do? It will take away, and actually not just one electron, a bunch of electrons. It will take away certain energy levels, certain colors, and you'll be left with almost everything except for a few missing colors. Can you tell me what kind of spectra this is called? An absorption spectra. So what I'm trying to explain to you is, how is an absorption spectra formed? When the electrons inside of the atoms, which make up the cloud of the gas, can absorb those energy photons. Then they jump to higher levels. Okay, so this is called an excited state because it's in a higher level, and it's unstable, which means the electron will not stay there very long, right? Sooner or later, what will it do? Where does it want to be? It wants to go back down to the ground state again. So now ask the question, how does the electron in one of these excited states, how does it fall back down to the lower level? By gaining or losing energy? By losing energy. So a photon which falls back down, in the process of falling, has to emit a photon of light. So the electron gives up light, but not necessarily in the original direction that the light was traveling. And so the cloud, so let's see, how do we show this? We've got this, let's say, stream of white light that's coming in here and coming in and hitting a cloud of material, right? If you look at the light on the other side, it's going to have missing colors, right? There's going to be missing colors right here. Almost everything. How do I draw that? Oh, yeah, there we go. Take away a few missing colors, right? And that's called the absorption. So this is continuous spectrum. And this is called the absorption spectra. Now, meanwhile, the gas got excited. And so it's going to radiate in all different directions. If you happen to be looking in one of these directions, you're going to just see the specific colors that got removed here. They're going to come out again. And what is this called? The emission spectra, right? Because the electron is emitting. Okay, so the electron can jump higher by, how does it jump higher? Absorbing a photon. How does it jump lower? By emitting a photon, right? Gaining energy. But it has to be just the right color of photon, just the right color of light. Okay, just the right frequency, just the right color. Okay? All right, so this is the idea of quantum physics. So we have the nucleus, which is where the protons and the neutrons are located. A proton is a positively charged particle that is inside of the nucleus. For a hydrogen atom, it's the only thing you have. A neutron is a neutral particle, that's all you need to know, with about the same mass as a proton. So you need to know that too, okay? Protons and neutrons have about the same mass. And the electron is a negatively charged particle that's attracted to the positive, which is outside of the nucleus, okay? All right, so there is something called the Bohr model of the atom. That's kind of what I just described to you, which is all these energy levels. The lowest level is level number 1, also called the ground state. This is the Bohr model. level 2, etc. So how do you go from the ground state to an excited state? By absorbing a photon. How do you go from the excited state back down to the ground state? By emitting a photon. Yeah. One more time.
The continuous spectrum?
The continuous spectrum? So that means that you're seeing all the colors of the rainbow with nothing missing. So that was what we were looking at today with our glasses when I turned on the light bulb and I changed the temperature a little bit. It was just all the colors, nothing missing. So continuous spectra is something that is emitted by a black body, by a hot object. So if you get light from a hot object, including you, right, you see all the colors, nothing missing. When that light passes through a cloud of material, certain colors will be removed. That's what we call the absorption spectra. But if you look, those colors come out in different directions, and that's called the emission spectra. So tomorrow I'll show you some emission spectra. I meant to showed you hydrogen today, but I'll show you a whole bunch of things, a few of them rather. Okay, excited state, emission, absorption. You guys got the words emission? What does it mean? The electron drops and emits a photon. That's emission. Absorption means the electron absorbed a photon and jumped to a higher energy state. Okay, the energy levels. Okay, so the word for jumping is transition. That's the word for jumping between energy levels. Okay, a transition. So a transition, listen to the words. A transition from n equal 1 to n equal 3. Did the electron absorb or emit a photon? The transition from n equal 1 to n equal 3. How did you do that? You absorbed a photon, right? You had to absorb a photon with just the right amount of energy. The transition from n equal 5 down to n equal 2. What happened to the electron? It had to emit a photon, right? It had to emit a photon in order to drop down. So it's that easy. If you jump higher, you had to gain energy. If you jump lower, you had to lose energy. And you have to lose or gain just the right amount of energy, the energy difference between the levels. Okay, so, oh man, Doppler effect. Who knows the Doppler effect? Did you read about it? You watched it? I know Phil told you about it. I actually have wanted to show you something. I went to Italy a couple years ago. Did I show you this video yet? No, I didn't show you. Okay, let's gonna watch a quick little video clip. It's very short, but it's meant to illustrate the Doppler effect for you. If you want to find it for yourself, it's on our website under pages, or under my, oh, it's under pages. Here we go. View all pages. Under links, useful links. Okay, Dr. Kelly. Here we go. Sean Kelly demonstrates. Okay, I apologize ahead of time. It's a little noisy. Okay, just like me, right? 21 seconds long. Okay, and so. Okay, hold on. Let me tell you something. So we're gonna observe the Doppler effect with a car horn, right? Which is sound. And the important thing is don't think about how the sound is getting louder. That's not the Doppler effect. It is getting louder, I agree. What you want to focus on is the frequency, okay? So if you listen to sound, there's high pitch frequency, higher frequency, and lower frequency. Any singers in the house? You know what I'm talking about, right? Higher pitch, oh, right, higher, oh, right, oh, right, you know, high, low, what, yeah, you got that. So what happens is the Doppler effect, the sound changes because it's coming towards you or moving away from you. That's it, right? So it's something that you have heard in the real world, and so we're playing a sound for you to make it kind of think about that. Okay, so my wife was filming me as I did that, and the farmers around there were like, what the heck is going on? Those Americans, you know, crazy Americans. But meanwhile, did you pay attention to the background? Right? Look at the beautiful sunflowers. Oh my God. Aren't they beautiful? I love them. They make you so happy. You're like, look at the sunflowers. Okay. All right. Okay. So again, we're being very qualitative. So when you write down, this is such a beautiful idea. And it's so cool because it works with sound and it works with light too. So write down Doppler effect. What's the key idea? If the source, we'll say it was sound first, but don't write this down. If the source of the sound is coming towards you, you do not hear the original sound. You hear a higher frequency sound. If the sound is moving away from, the source of sound is moving away from you, you do not hear the original sound. You hear a lower frequency sound, okay? That's the Doppler effect that you just observed by watching that little video. Now, the most amazing thing, it works with light too, okay? So I have a star. If it's coming towards us or away from us, we will literally see the colors change. Are you ready? So we want to know, Doppler effect means it works for light. If the source of the light, whether it's a nebula or a star or anything, if it's coming towards us, what will happen to the color of the light? It will shift to a higher frequency, okay? Now you want to write down, Doppler shift, higher frequency coming towards you. In astronomy, we give it the name a blue shift. It's a quick way to say Doppler effect, because it's coming towards you, it's shifting to higher frequency. We call that a blue shift. It means towards higher frequency, okay? So one more time. A source of light is approaching you. You will not see the original color. You'll see it shifted to a slightly higher frequency. The color will not be exactly as it was, right? And the same idea, if it's moving away from you, what will happen to the frequency? It'll be a little bit lower, and the name we give that in astronomy is called a red shift, okay? So blue shift, red shift, right? Blue shift, red shift. Okay. Blue shift means what? Blue shift? Blue shift, coming towards you. Red shift, moving away from you. And the amount of the shift tells you how fast they're moving towards you or away from you. We don't have to worry too much about calculations, but that is the case, okay? So the greater the blue shift, the faster it's coming towards us. The greater the red shift, the faster it's moving away from us, okay? All right, next word, inverse square law for light, okay? So this is a topic that we did not cover, but we did cover inverse square law. Okay, did anybody remember what formula has the inverse square law in it? The formula for gravity, okay? The formula for gravity. If you remember it, it has m1, m2 over the distance squared. So if you make the distance get bigger, the gravity gets weaker according to the distance squared. Okay, so double the distance, what happens to the force of gravity? We said it's going to be 1/4 as big. Okay, so a new formula, a new idea. In astronomy, when we measure how bright a star is, we have a name for that, it's called magnitude. But anyway, if you measure the intensity of the light that's coming from a star, we have a new word here, it's called the brightness. The brightness of a star. And I'm going to write the formula down because I don't really have any other options. It's got to be something, so this is what it is. The brightness is big L. Remember what L stands for? The luminosity of a star, divided by 4 pi d squared, okay? So d stands for what? The distance to the star. How far away is it? L is the luminosity of the star. How much light comes out of that star? And then the other thing is, how far away is the star? Okay? Everybody got it? There's two letters that are important here. And this 4 pi d squared, do you recognize that? It's a surface area formula. And the reason it works is this is what's happening. You have a star very far away, right? Which direction does the light shine? Which way? Every way, right? It goes in every direction. So if I imagine the pulses of light energy going away from the star at the speed of light, I can kind of imagine that each pulse of energy, if I'm a distance d, is being spread over a bigger and bigger sphere. The further away I go, the more that energy has to be spread out. So the intensity of the light gets decreased. This is actually a formula for intensity, okay? But again, we don't do that in our class. It's just that's what it is, Okay? So as you spread it out more and more, it gets smaller and smaller intensity the further away you go. So what we're going to do is compare two stars, and we're going to compare their brightness. Okay, so we have a star, the same star, L is the brightness of the star. We have the distance here. This is our first distance. And then what happens if we go, I don't know, I mean, I always do twice. Let me do more. Let's do like 3 times as far. Okay, so 1, 2, 3 times as far. Okay. Okay, so I'm here, right? So instead of D, how far away am I? I'm 3 times D, right? Same star, L. What happens to the brightness? Brightness 1 and brightness 2, right? The brightness over there, we'll call it brightness 1, and over here, brightness 2, right? So the formula is L divided by 4 pi d squared. I don't know, whatever that is, right? But how is this one different? Is it bigger or smaller? Bigger or smaller? The further away you get from the star, what happens to this brightness? It gets smaller, right? The further away from the star, the dimmer the star will be, okay? And so you write L over 4 pi, but this time I have to put 3d squared, right? What gets squared, the 3 or the d or both? Both, right? So how does this brightness compare to this brightness? It's almost the same, except it has that extra 3. So how is this brightness compared to this brightness? It is 1/9 as big, right? 1 over 3 squared, which is 9. So the brightness 2 is 1/9 as big as the original brightness, okay? So I realize this may be kind of hard, but you're going to have to do it tomorrow, so do your best, okay? I'll give you another example in a second. Actually, let me do it right now. Let me do another example right now. In fact, I'm giving you a heads up. You guys are here. You obviously want to do well. I'm going to tell you about a problem on your test tomorrow, okay? You ready? Okay? It's not that hard, but that's what it is, okay? So there's this thing called a light bulb. Everybody know about a light bulb? Ooh, I got to move my, thank you. Those people at home don't really need to know what's going on. Oh, yes, I care about you too. Okay, let me move the projector to the other side. Okay, so this thing called a light bulb. Everybody heard about a light bulb? Just kidding. Okay. All right, you ready? I'm going to give you a real problem. It's a little bit different than the one on the test, but the same idea, okay? So we have a light bulb, and let's say it's a pretty bright bulb. Anybody know the number that would be with a pretty bright bulb? Anybody know light bulbs? Raise your hand. I know light bulb. No? Never heard of a light bulb before? Okay. Come on, give me a number. 100-watt bulb is actually pretty bright. Everybody heard of a 100-watt bulb? No? Okay. Okay, the power of a bulb is exactly the same concept as luminosity. Same idea. They're the same. Power, luminosity, same idea. So I could write down 100 watt. So here's my bulb right here. Now I'm going to do the following experiment. I'm going to look at the bulb from a distance of 1 meter, right? And I'm going to ask myself, hey, how bright is that bulb? And the answer is, well, I already know. It's a 100-watt bulb. I'm 1 meter away from a 100-watt bulb. That's a 100-watt bulb because I just looked at it. I know it's a 100-watt bulb. Okay? Everybody good? So it's some intensity. I don't know what it is, but I don't really care. What I want to ask next is, if I move to a distance of 10 times as far, 2, 3, 4, 5, 6, 7, 8, 9, 10. There we go. 10 times as far. 10 meters now. Is it going to be brighter or dimmer? Obviously, it's going to be dimmer, right? Everybody, you're 10 meters away now. It's all the way across the room. It was 1 meter from you, holding it at an arm's length is like 1 meter, and now it's all the way across the room. So it doesn't look the same anymore, right? How does the brightness here change? Okay, so this was, I mean, I actually could have calculated it, couldn't I? I actually could have done it. I could have put in 100 watts, I know that. I didn't need, this is too much math. If you like this, take astrophysics, okay? And 4 pi, 1 meter squared. Actually, I don't care. It's just a number, whatever it is, okay? But I want to come over here and ask the question, how does it change when I look at it? And the answer is, it's still the same 100-watt bulb, but now, what am I dividing by? 10 meters squared. So what does it look like? Well, the only difference between these two is you have a 10 here. So it's actually going to be 1/100th of the original brightness. So here's the way the wording of the question will be, right? If I look at a 100-watt bulb from 10 meters away, what does it look like? And I want you to go back and say, if I were standing 1 meter away from what wattage bulb? It looks like I'm holding a bulb which is only how many watts? So it was 100 watt divided by 100. What does it look like? A 1 watt bulb. So a 100-watt bulb, 10 meters from it, looks like a 1 watt bulb 1 meter from it. Because this factor of 100 can be divided here, changes it into a 1 watt bulb, right? And then I have, all right, that's confusing, isn't it? Okay, so figure it out. Okay, all right, let me say it one more time. Okay, I could do a little more math, but I don't want to do a lot more math. I want you to get the idea that if you go 10 times as far, then there's a factor of 100 in the denominator. So what's 100 over 100? Is 1, okay? So then this stops being 10 anymore, right? It's back to being 1 meter again. And so if I look at that, let's put 1 watt. Okay, so, sorry, let me do the math. Okay, I'm doing the math. Okay, if you take this 100 and cancel this 100, then you get 1 watt over 4 pi times 1 meter squared. Okay, so that's exactly the same as this, except replace the 100 watt with a 1 watt bulb. So in other words, when you get 10 times as far, it doesn't look like a 100-watt bulb anymore. It looks like a 1 watt bulb. But the reason is because you're so much further away. Okay, so the brightness of a bulb has to do with partly how much luminosity, but secondly, how far away you are from it. Okay, so do your best. There's a question on your test. It's a little easier than that one, frankly, but it's the right idea, okay? So the further away you get, the weaker it looks. The closer you get, the brighter it seems to be. Yeah? It looks as though it's a 1 watt bulb when you go 10 times as far away from it. So originally you were 1 meter, and then you went 10 times as far. As a result of going so much further, the brightness was decreased by a factor of 100. Now that 100-watt bulb kind of looks like a 1 watt bulb held at 1 meter away. Okay, so you're not actually holding a 1 meter away a 1 watt bulb, but that's what it looks like, the same brightness as it would be. All right, so the next section, by the way, is all about telescopes. Okay, so this is stuff I did not cover. It's very quick, very easy, because we do not go into a lot of detail. So should I just bring up the slides, do that? Or should I just talk about it? What do you think? Just tell you about it? Okay, I'll tell you about it. Okay, it's pretty easy. Aperture, that's easy. It's not that hard. Aperture is the opening that lets light come into a telescope. And there's something important you want to know. Bigger is better. We want to have more light. The more light you collect, the more you can see, okay? The hardest part about astronomy is so many things are dim. They're really hard to see. So bigger opening means more light can come in. And actually, specifically, it's going to come up in a little bit. The light collecting power of a telescope is based on the size of the opening and the mirror that goes with it or the lens that goes with it. So the aperture kind of determines how much light you can let in. And the size of the opening or the shape of the opening is a circle. So it turns out to be a very simple formula. So the area of a circle is something many of you probably recognize. The area, the size of an aperture is a circular opening. And who knows the area formula? It is pi r squared, okay? So you need to know that the r squared is the part that's important. So if you make it bigger, it gets better, right? But how much better, right? So if you make it 3 times as big, how much more area, how much more light will come in? And the answer is, well, you have to square that factor of 3. So the answer is 3 squared, 9 times as much light comes in. If you make it 10 times as big, right? And that's a big telescope, then you will get 100 times as much light coming in. Okay, you're using the R squared. So the bigger telescope collects more light. That's the key idea. So bigger is better or not? You want more light? Yes. Okay, as much as you can afford. Okay, and that really is true. If you ever want to buy a telescope and you have a choice between something with a high magnification or a big aperture, go with the big one. Okay, big aperture, more light. Okay, that's going to be more fun. Okay, so angular resolution is actually, you guys are using computers and stuff, you have phones. Angular resolution is the ability to see a little detail, right? How fine a detail can you see? It's the resolution, right? How sharp a picture is it? So it is based on a very simple concept that when we look up at the sky and we see things, we actually see how big they are, not really in size necessarily, because they could be very far away from us. We see the angle that they make. So the angular resolution is the ability to tell that two objects that are within a certain angle are actually two objects. And it's kind of like the idea if you're driving on the highway and you see headlights coming towards you down the highway, if they're very far away, you can't tell that there's two headlights, just one blob of light. But when you get finally close enough, you see, oh, there's two headlights. You have now resolved that there's two headlights. So angular resolution is the ability to see that two objects are actually two objects and not look like one. And as a result of this, the picture gets sharper. You see more detail. So in astronomy, we want to have a nice sharp picture, right? We want to have a lot of detail if possible. Angular resolution, the ability to see that two things are separated from one another. Okay, so we have two kinds of telescopes in this world. One of them is called the refracting telescope, and the other is called the reflecting telescope. And actually, it's just too easy. Let me just put up some pictures. Refracting telescope. Look at that. I got a million pictures here. A refracting telescope, refracting telescope. That's what I want. Okay. Oh, it's too complicated. Here we go. Simple. Keep it simple, man. All right. So how do you make a refracting telescope? You use lenses. It has pieces of glass or plastic, and they refract or bend the light. Okay. That's a refracting telescope. So you got one piece. The main lens is called the objective lens. You don't really have to know that. Unless you're in the lab, you have to know that. Okay, and that's the collector of the light. So the size of the opening, the size of the objective determines the amount of light. And then the one that you look through is called the eyepiece, okay? So those are both lenses. They are bending light, they're refracting light. The other major kind of telescope is called a reflector. That's it. Okay, there's only two kinds, refracting and reflecting. For now, there's going to be more in the future, but for now, that's it. I know I shouldn't tell you that, but that's the truth. Okay. Okay, there we go. That's the Newtonian. Okay, all right. This is more like the ones we use in the lab. Let me look at that picture. So you got a big mirror at the back of the telescope. This is the aperture, the opening. But the size of the opening matches the size of the mirror. So what you do is the light bounces because the device that's catching the light is a mirror. Okay? So a reflecting telescope uses a mirror as its primary element for gathering light. So same idea, larger mirror, more light, better picture. Okay? So two kinds, reflecting, refracting. Everything is one of those two. Okay, so I put eyepiece magnification. These are just words. Okay, so what's the eyepiece though? The piece that you look through. Okay, pretty easy. Don't go crazy. Magnification is something that you can change by changing your eyepiece. Okay, so there's actually a kind of a formula. I don't think you need to know that. What it is the making things bigger. Magnification, making things bigger. So you can control the magnification of a telescope by changing the eyepiece. That's the only thing you need to know. Okay, chromatic, any questions? You got those pieces? Reflecting, refracting, we got that. Eyepiece. Okay, here's a word, chromatic aberration. So if you remember, with white light going through the prism, what happened? It spread into all the colors of the rainbow. Now, what does it mean? It means that different colors of light refract different amounts. So if you're looking at something that's very colorful and you put it into a refracting telescope, not all the colors bend the same amount. So what happens is that one color will be focused, but the other colors will not. So what happens to the image? It looks kind of blurry. So chromatic aberration is the idea that different colors get bent different amounts, and therefore the picture can look kind of blurry. You like that? No, nobody likes that. So what Newton discovered is that you use a mirror, and mirrors reflect light just the same way every time. They don't have the same problem of chromatic aberration. So the benefit of a mirror, a reflecting telescope, is it doesn't have to bend the light to collect it, and therefore it has less of an issue with that chromatic aberration, almost none. Okay, jumping to the next spot. Okay, atmospheric transmission is the, yeah, question. Chromatic aberration. Different colors of light refract different amounts. So in a telescope, one color will be focused, but the other colors will be not focused. And so they don't pass through the telescope in the same way. So the problem is that the picture appears blurry. So it's the blurriness that is caused by this effect that different colors bend different amounts. So we call it an aberration, chromatic aberration. Chroma means color, chromatic color aberration. So if it was just one color, you wouldn't have a problem, but it's many colors that is the problem. Okay, atmospheric transmission. I feel like I need to just bring up the slide on this because that's actually better than what I'm going to say. The atmosphere of the Earth absorbs a lot of the colors of light, but not in the visible part of the spectrum. Okay. So the atmosphere of the Earth turns out to allow some colors to pass through and others to not pass through. And it's kind of an interesting thing we'll learn more about. All right, here we go. So here's a picture showing the wavelength of light and then the atmospheric opacity. That's a word that we haven't talked about, but opacity means blocking light. It blocks the light. So if it's high, it means the light cannot get through, right? So what you want to know is that if you want to look at the universe, there are actually only a couple kinds of light that can get through the atmosphere of the Earth. And therefore, on the surface of the Earth, we can only do a couple of kinds of astronomy, only a couple kinds. So one of them you want to notice is that the light, which we call visible light, the opacity is very low. What does it mean? Most of the visible light gets through the atmosphere. So can we use visible light telescopes from the surface of the Earth? The answer is of course, right? That's what the lab does, right? We use light telescopes. We see the light. So visible light gets through the atmosphere. What about, if you jump over here, what about radio waves? The other kind of telescopes that you can have are called radio telescopes. Everything else has a high degree of opacity. It means the atmosphere absorbs it. And there are places where it's being absorbed. I don't think we have to worry too much about that. It's actually a good and a bad thing, right? Probably bad for astronomy, but good for living, right? You like to be alive? Okay, you're happy that the atmosphere of the Earth protects you. Because remember we talked about that ultraviolet light, for example, right? You remember that stuff? Most of it is being blocked by something you probably heard about called the ozone layer. How about that, right? So do you think you would like a world where there was no ozone layer, right? That would not be so good for life. I mean, we might be able to evolve to handle the mutations of our DNA, but it would probably be bad. Most of us would die. Okay, it's not a good thing. So the Earth protects us from a lot of things. Lots of these high energy photons are blocked, but here's infrared. So I'll just tell you two things. Okay, two things. The ozone layer blocks most of the ultraviolet, and then I want to tell you about the infrared. Okay, the infrared is blocked by something else in our atmosphere, and that is water. The water in our atmosphere is really good at blocking infrared light. Okay, so some things can block certain kinds of light while letting others through. For example, have you ever looked through a window? Right, I'm just kidding, right? You look through a window, And you can see the light coming through, but guess what? The window doesn't allow infrared light to pass through. It blocks most of the infrared light. So it can allow one light through. It's transparent in that frequency and be opaque in another frequency. All right, so that's the idea there. Okay, why do stars twinkle? Somebody asked that, right? Why do stars twinkle? The twinkling is actually refraction, the bending of light, the splitting of the different colors by turbulence in the atmosphere. The atmosphere is like little lenses that's bending the light, right? And changing the direction of the light just slightly. So that's why stars twinkle. They twinkle more the lower you get in the atmosphere because they have to pass through more atmosphere to get to your eye. When they're up high, they don't twinkle as much. Down low, they twinkle a lot. Okay, telescopes are placed on mountains. Why? To get as high as you can to have as little atmosphere between you and space. Okay. All right. So, wow, that's a lot of stuff to cover. Good luck tomorrow. Okay. I'm just kidding. Here we go. Let's see. Okay. So I pretty much talked about a lot of things. Oh, a lot of things. Okay. So I was going to show you a picture of atmospheric opacity, adaptive. Okay. So let's talk about real quickly radio telescopes. Okay, here's a picture, radio telescope. These are radio telescopes, right? You can see they're made of metal, but they have lots of holes in them. And that's okay because they're trying to catch radio waves. Radio waves are very long. And so those holes are almost invisible to the radio waves. The radio waves see this as solid, right? They don't consider it to have holes. That's an interesting idea. That's why your microwave oven, you can see through. That grid of metal blocks microwaves, but not visible light. Okay, you can see through and see the food cooking. Okay, the other thing is radio telescopes are not often by themselves. They're connected together in what we call an array. I mentioned this to you guys almost on the first day. So radio telescopes don't come singular. They come with a whole bunch of them. And the reason why is we have the technology today to connect them together. This is called interferometry. So interferometry is an amazingly cool tool. So let me just demonstrate. Actually, I probably find it. I don't know where it is. Let me just draw. Okay, this is the idea. Interferometry. Let's suppose, and actually we've done this now to take the picture of the first black hole. That was done, right? In fact, amazing how they did that. But if you have an array, you have a set of telescopes arranged along a setup like this, right? You only have 9 telescopes here. They are connected together electronically, and they act as though they are this big, right? As if you had filled in all that space. That's pretty cool. It's a lot cheaper than having to fill in all that space, but they work like a telescope that big, right? And what happened recently with the picture of the first black hole accretion disk is here's the Earth, right? Here's the Earth, and they did the same thing. They linked together telescopes across the Earth, and so it acted as though it was a telescope that big, okay? Pretty amazing. This is something that had never been done before, so you want to appreciate not necessarily just the picture, but also the technology that made it possible. Okay, so that's called interferometry, and our final terms, we're getting close to the end of that chapter. Wow, it's a long chapter. Here we go, is adaptive optics. Okay, don't need to know a lot, but let's say that what you need to know is that when light comes through the atmosphere bends and changes the direction of the light and sometimes makes the picture blurry. But we have the technology today to understand what the atmosphere is doing and then mathematically undo it. And so there's a really amazing thing. The adaptive optics uses a laser. They shoot a laser up into the air, and they watch how the laser gets distorted on the way out, and then they undo mathematically what's happening when the laser goes through the atmosphere. So it allows you to change the picture. Now, there's a little bit more. They actually have the ability to change the shape of the mirror, right? So the adaptive optics has 2 pieces, an electronic component, and also it can change the shape of the telescope itself. So that's all you really want to know, is there's a way to compensate for the disturbance of the atmosphere by changing the shape of the mirror and also electronically compensating for the atmosphere. All right, so I talked a lot. I think we will just skate right through these, I hope, because otherwise we didn't get a lot done. Describe how the energy of a photon relates to the frequency. How does it relate to the frequency? Higher frequency equals higher energy, right? They're directly proportional. More frequency, higher energy. It's directly proportional. Double the frequency, double the energy. How about wavelength? Higher frequency means shorter wavelength. The shorter the wavelength, the higher the energy of the photon will be. That's the connection we're talking about. Describe how you get the spectrum, the 3 different types of spectra. The names were continuous. How do you get a continuous? From a hot body, blackbody radiation. How do you get an absorption spectra? Take that light and pass it through a gas cloud. On the other side, it will have some colors missing. That's called the absorption spectra. Look to the side like we did over here, and you will see just the colors that were just absorbed, they're going to be coming out again. And that's called the emission spectra. They're called Kirchhoff's laws. Okay. There we go. Okay. And not a Mac guy. Okay, here we go. All right, describe how blackbody spectrum is affected by the temperature, okay? What happens? When you increase the temperature, where does the peak go? Towards higher or lower frequency? Higher frequency. What happens to the size of the peak when you raise the temperature? It gets bigger, right? Dramatically bigger. Those are the 2 things you need to know. Okay, describe how an electron can jump to a higher energy level. How does the electron jump higher? Absorbing a photon. How does it jump lower? Emitting a photon. Done. Okay, explain how the light of a star changes with respect to distance from the star. So that was the concept of the brightness. The further away you go, what happens to the brightness? The lower the brightness, the smaller the brightness will be. If you go twice as far, what happens to the brightness? You're supposed to remember 1 over distance squared, right? So you go twice as far, 1/4 as big. Yeah, 4 times dimmer, right? 1/4 as much brightness. Explain how the size of a telescope changes its light gathering ability. The formula is pi r squared. So if you make it 5 times as big, how much light can it gather? 25 times as much light. Pi r squared. I keep doing that squared thing. Do you guys notice a pattern? We get that a lot. Okay. Oh man, I threw this in here. Okay. Oh, little tiny detail. I threw that in there. Okay, in the book, they describe something called angular resolution. There's a formula, and so it's going to be pretty obvious, but one part is not, one part is, okay? The angular resolution, the ability to see detail, has 2 factors. One of them is the wavelength, and the other is the size of the telescope, the diameter of the telescope. So if you want better resolution, one solution is get a bigger telescope. That's the obvious one, right? The size of your detail gets smaller, right? The larger your telescope. It has an inverse relationship. Larger telescope, smaller detail. But the wavelength is also a factor. So it turns out that if you just have a certain telescope and you can choose which color to look at, which color will have the greatest resolution? The longer wavelength or the shorter wavelength? Well, the answer is the one with the shorter wavelength. So in the visible part of the spectrum, you have Roy G. Biv, all those colors to choose. If you use just one color, which color will give you the highest resolution? And the answer is the smallest wavelength, violet. Okay? So the red picture will not be as sharp as the violet picture will be. Okay? And don't worry about anything else. This is a little bit of a detail. I'm sorry I put that in there. Whatever. It's there. Okay, explain why some types of telescopes can be found at the surface and some have to be flown at a high altitude or in space. And the answer is the atmosphere absorbs most of the light, right? Most of it. And we said two particular things. The ozone absorbs ultraviolet and the water absorbs infrared. Those 2 for sure we can't do at the surface. So what can you do at the surface? Visible and radio, okay? Explain why radio telescopes are often found as part of an array. And the answer is interferometry, right? They can be linked together and act like a single telescope. And that means it's a much larger telescope. The order of the colors and Roy G. Biv and the range, okay, something you're going to need to do. Okay? All right, so now what I'd like to do is take a few minutes and do the 5 questions so that you can hopefully, now you should understand them if you didn't before. So let's take a look at those 5 preview questions. Don't forget to do them because that's how you get your extra credit, okay? So you don't get the extra credit if I do it. You get it if you do it, okay? But I'll go over them with you right now. Preview. Oh, man. Okay, sorry. Let's... Too much. Preview. Here we go. Are you ready? Take the quiz. Okay. Anybody already do this? Figured it out? Okay, good for you. Okay. Okay. Ooh, this is a good question. This is a hard question, but I'm giving it to you, so it shouldn't be hard anymore, okay? Please. Okay, star A is 4 times more luminous than star B, but it is also 4 times as far away. How does the luminosity, how does the brightness of these 2 stars compare? The brightness formula is B equals L over 4 pi. Oh, it's 4 pi. Oops. Oh, well. I should say pi. Oh, well. Oops. I didn't notice that. Oh, well. It doesn't matter, right? We don't actually care about the pi, right? We don't do any calculations in this class. Okay, so the brightness, I'm going to show the people at home. Okay, anybody know how to do this? Got an idea? Okay, so it's supposed to not to be that hard, but let's see if we can do it. Okay, so let's do this, right? Let's write down what they told me, right? They said the luminosity of star A, here's the luminosity of star A, is 4 times the luminosity of star B, right? 4 times. And then what else did they say? The distance to star A is also 4 times the distance to star B. Okay, and let's try this out. So how do you get the brightness of star A? Let's try that. Okay, so you take the luminosity of star A divided by 4 pi times the distance to star A squared. And how do you find the brightness of star B? You take the luminosity of star B divided by 4 pi, the distance to star B squared. Okay, so if you look over here, these things tell me how they're connected, right? And so what you do, and if it's hard, I'm sorry, but I'm showing you now, so it shouldn't be hard, right? Is you substitute in right here, and you substitute in right here the quantities, right? So when I rewrite this, I get 4 times the luminosity of B, right? I just put that in. And I have this 4 pi, and I put in 4 times the distance of B squared, right? So this 4 should have made it bigger, but this 4 gets squared and is in the denominator, should make it smaller. Which one is the more important factor? You got 4 on the top, but what's 4 squared? 16, right? So if you take away those 2 things, you get 4 over 16. What are you left with? The luminosity of B over 4 pi, the distance of B squared. Well, that's just this right here. So in other words, this is the fraction that we need to worry about. What's 4 over 16? 1/4. So A is brighter or dimmer? It's dimmer. It's 1/4 as bright. So what's the right answer? The answer is not 1/4. What does it say? 4 times dimmer. 4 times dimmer, right? I apologize. That doesn't sound really good, but that's what it is. So 4 times fainter means dimmer. Okay? All right, first question. Whoa, these are hard. That was hard. That was hard. Okay, that's as hard as it gets. Which of the following can be seen as a crescent phase from Earth? Most of my students last time did not remember this. Can all the planets be seen with crescent phases? No, only the ones that are closer to the sun than we are. So that means what? Mercury and Venus. Ooh, tough one again. Most people just looked at the numbers and are like, ooh, ugly, I'm not going to do that. And it's not that hard. That's the part. A satellite is originally at an altitude of, a distance of 10,000 kilometers from the center of the Earth, right? 10,000. That's the radius of its orbit. And then we move it to a new orbital distance of 20,000. Now, I want you to say to yourself, how did I change it? What did I just do? I went from 10 to 20,000. I doubled it. That's it. So that's all you have to say. If you go twice as far, what happens to the force of gravity? Stronger or weaker? Yes, weaker. By what factor? 2 squared. Don't forget that, right? So the answer is it will be 1/4 as large, right? 1/4 as large. Okay. Again, that's kind of tricky, but not that bad. Oh, I can't believe I'm giving you this one, but this is, again, one of the ones they missed. It was a waning gibbous tonight. In 7 days, what will it be? So you have to think to the next. It's not a quarter or a new moon. It's a waning gibbous. What comes after waning gibbous? Third quarter, after third quarter, waning crescent. So what would it be in 7 days? A waning crescent, okay? Waning crescent. If you're not sure about that, you probably need to study that a little bit more. There are a couple more questions on moon phases, okay? So please be able to do that. Okay, cool. A gas cloud has an emission spectra. If all of the lines of color appear at a higher photon energy than compared to the laboratory, what would you say about the cloud? Does everybody recognize this is the Doppler effect? The Doppler effect, right? The energies were shifted to a higher energy. Why is that? The cloud is moving towards us or away from us? Which one? Towards us, right? So that's the answer. The cloud is moving toward the observer. Okay? Let's make sure I got 100%, huh? Wouldn't that be funny if I didn't? Haha. Oh, yeah. Okay, good. All right. Okay. Okay, so we've gone back, and let's see if we can go forward back. Okay, do you guys want to do 3 and then to 1, or just go straight to 1? Should we just go straight to 1? 1, 2, 3. Okay, 3. Okay, let's do 3. We're going backwards. Okay, fine. Actually, this is good stuff. This is probably the harder stuff too. So, okay, Kepler's laws of motion. Hold on, Kepler's laws. Okay. How many laws are there? 3 laws. Okay. Law number 1: the planets move on ellipses with the sun at one of the foci. Okay. The ellipse can be more stretched out or less stretched out. The word for that is eccentricity, right here. More stretched out, the number is larger. Less stretched out, the number is smaller. A perfect circle, the eccentricity is 0, right? And so the bigger it is, but it can't get bigger than 1. So it's a number less than 1. Okay, ellipse foci are the centers of the ellipse, right? So instead of a single center like a circle, right, an ellipse has 2 centers called the foci. The major axis means what? The longer axis. The longer axis is major, and then cut it the other way is called the minor. Half of the major is called the semi-major. It's really silly, but anyways, that's it. Okay, conservation of angular momentum. I actually was supposed to talk about this, and I didn't. So you guys want to know that Kepler's law means conservation of angular momentum. The reason it works, he didn't know why it worked. He just recognized it. I'm sorry, not the first law, the second law. The reason the second law works is because of conservation of angular momentum. So the idea is that in the same way that we said conservation of energy, energy cannot be created or destroyed, only transformed. Conservation of angular momentum says a body cannot change angular momentum unless someone gives or takes from it, right? So if it has a certain amount of angular momentum, it must keep that certain amount of angular momentum. Okay, so the way that we're going to see angular momentum in the future is the idea of an ice skater. Okay, so if you guys ever watched ice skating, someone is going to do a spin. They're going to spin, right? You're about to see them spin. Just before the spin, they have their arms outstretched, right? And then they start their spin, right? And then what do? They pull their arms in really close. And what happens as a result of that? They spin up really fast. That is called conservation of angular momentum. The reason it works is conservation of angular momentum. When the mass is located far from the axis, it's harder to make it rotate. And so the object rotates slower. Right? When the mass is close to the axis, it's much easier to make it rotate, and so it ends up rotating faster. So again, you're not taking a physics class, just try to get there's an idea behind this. It's called conservation of angular momentum. Let's jump to the second law, and let me see if I can help you understand why it works. So the second law, the law of equal area, right? In equal time, the planets sweep out equal area in equal time. And I use pizza analogy, right? What's different about the pieces of pizza? They have the same amount of cheese, but different amounts of crust, right? And that was the key thing. So what does it mean? Why do they have different crusts? Same amount of time, but different distances in that time. And so it tells us that the planets travel at different speeds, okay? And so you need to know, that's the real cool thing, right? The planets travel at different speeds when they go on these elliptical orbits around the sun. The two words you have to keep in your head are perihelion and aphelion. Now let's say the words together and what happens, right? At perihelion, you go fastest or slowest. At perihelion, you go fastest. At aphelion, you go slowest. And the reason is conservation of angular momentum. So again, we didn't study that, but this is the reason why it works, okay? So behind the scenes, if you're a physicist and you say, what about the angular momentum? The answer is the system always has the same amount of angular momentum. All right, I cover most of this. Okay, orbital period, what does that mean? The time it takes to go once around the sun. Orbital period, right? We're talking about planets in this case. If we're talking about Kepler. Oh, I forgot the third law. Let's do the third law. What is the third law? Because that's the one that most people have trouble with. And I didn't give you any examples, like a preview. So that means all my students did well on this. You're supposed to do well too, okay? Which means I've given you most of the examples you should worry about. But the third law is the one that's a formula, okay? What is the formula? The third law, P squared equals A. What's A represent? The semi-major axis cubed, right? Okay, so we'll do another example. Why not? Throw another example. Just to remind you, we have done a number, if you look in your notes. Let me do another example that I didn't do before. I did this with you, Angelica. I did that, right? Yeah. Let me do Saturn, which is at a distance of 10 AU. Okay, Saturn is at a distance of 10 AU. Saturn, being at a distance of 10 AU, takes much longer to go once around the sun, more or less than a year. And it's much further away, much more than a year, okay? So it's 10 AU. So we're supposed to use this formula to calculate some reasonable number for how long Saturn takes to go once around the sun. So what did I give you? I gave you the A. You're expected to find the P. So P squared equals, you have to be able to do this, 10 cubed. That means 10 times 10 times 10. What's 10 times 10 times 10? 1,000, right? So there we go. Okay, everybody knows the square root of 1,000, right? Just kidding. I didn't think that you would. If you do, that's awesome, but I'm not expecting you to know that. So you're going to have 4 or 5 answers, and you're looking for the reasonable answer. So I'm going to give you this advice. Pick a nice round number and see which one is closest to the answer. So for example, what about 10? 10 squared is 100. We're not even close. How about 20? In case you forgot how to do this, 10 squared is 100. Because you take 1 squared and add 2 zeros. That's how you do it, right? 20 squared, who could do that? 20 squared is, 2 times 2 is 400, okay. 30 squared is 900. Ooh, we're getting pretty close, okay. 40 squared is 1,600. Oh, that's way too big. So which one's closer? 30 or 40? So if you saw a bunch of answers, right, you see 19, 26, 32, 41, 55. Which one pretty much is the right answer? It's got to be. Okay, does everybody understand? That has to be the right answer. It's the only one that's close to 30. Okay, 30 is much closer than 40. Does that make sense? Either that or you just try it. Okay, try to square this number. You get 1,000. I mean, I know it's a lot of work. Okay, but 19 is less than 20. 20 squared is 400. I don't know. You got to find a way. Love will find a way. Okay, do your best. More examples? Should I do one more? One more example. Okay. Suppose I give you P instead of A. Let me give you another one. Suppose I want to design the perfect spaceship. I don't know. The perfect. Okay, I got it. I got a good one. I got it. Suppose I want to create, because my favorite number, one of my favorite numbers is pi, right? Actually, at 3:14 every day, I stop and celebrate pi time. Okay, never mind. Okay. Oh man, I'm gonna make the period be pi. All right, never mind. Let's say the period is 3 years. Okay, just for fun. Not pi, but I could do pi, but let's do 3. Okay. So how does it work? Trying to find the radius of the orbit, semi-major axis. Okay. So 3 squared equals a to the 3rd power. What's 3 squared? 9. Okay. So again, I'm going to try to use numbers that make sense and see what I can come up with. So let's say that I try 1 cubed. Well, that's just 1. That didn't work. How about 2 cubed? 2 times 2 times 2. Oh, pretty close. Okay. 3 cubed. Let's try that. 3 times 3 times 3. Okay, 27. Anybody want to guess what the number must be? Really close to 2. Right? Would 2.1 surprise you, or 2.05 or something? That wouldn't surprise you. It's going to be really close to 2. I don't know what the number is. I don't care. I just want you to see it's got to be really close to 2, because 2 gives me 8. 3 is way too big. So the answer must be very close to 2. That's how good you have to be, just like that. All right? See you tomorrow, Serena. Okay, so back to that. Okay, so Galilean moons, who knows the names? 4 Galilean moons that go around what planet? Spotted by Galileo. What are their names? Closest. Io. Second. Europa. Third, the biggest one in the solar system. Ganymede. And 4th one, Callisto. Callisto, very good. Mass, okay. I'm jumping right now into, this is, by the way, Newton. It's going to be Newton in a second. Mass means what? How much stuff, right? How many atoms are there? The more mass, the harder it is to change its motion. Mass is also called inertia. Okay, force, what's a force? A blank or blank? A push or a pull? It has a strength, a magnitude, and also a direction. You have to remember that it has a direction. And velocity, what's velocity? How fast you're moving, speed, plus the direction, right? So velocity is the speed and the direction put together. And acceleration, what's that? It's the rate at which you are changing your velocity. You have to say the word velocity this time, okay? So when you change your velocity, what does it mean to change your velocity? Does it mean changing your speed? It could be changing your speed, sure. How do you change your speed? Well, make it go faster, make it go slower, speed up or slow down. Those are 2 ways to change your speed. But velocity, because it has direction, means that you could also change your direction. Okay, so how do you change velocity? By speeding up, by slowing down, or by changing direction. That's it. There's nothing else. Okay. Now, could you speed up, slow down, and change direction? Yes. Okay, you can have 2 of those things, sure. But the idea is you're changing one or more. You're either changing magnitude, speed, or direction, or both. And if you do, sorry, one more time. If you change your velocity, you accelerated. If you accelerated, a force caused it. Right? These are all true. They have to be true. Okay, so, I put the word vector. Oh, thank goodness. I've been trying not to say the word vector, but I put it up on the study guide. You have to know what a vector is. Gosh, why didn't I just tell it to you the other day? A vector, ladies and gentlemen. Okay, audience at home. A vector is an arrow. That's it. A vector is an arrow. Anything that you can draw as an arrow is a vector. Okay? So vectors are drawn as an arrow. Okay? A vector is a quantity in science. A vector, you might have heard this word before in other topics, like sometimes they talk about the virus vector. How did it infect the population? It's kind of related, but a little bit different. All right, vector. A vector is a quantity that has magnitude, which means size, and it has direction. And so the beautiful thing is you can draw it as an arrow. Okay? So I'm going to draw an arrow for you. This is an example of a vector. Okay? So here's a vector, and there are lots of things that can be vectors. That's an example of a vector. Okay, what is it? Okay, maybe it's 3 meters per second. Anybody want to tell me what kind of vector it is? Meters per second is a speed, and there's a direction to the right. What would this be? This is a velocity vector, okay? Because I put the 3 meters per second there. So velocity is a vector, okay? So the examples of vectors that you want to know, velocity, acceleration. Anybody think of another one? There are so many, but I'm just going to do a few. Force. Anything else? How about mass? Is mass a vector? No. Mass has a magnitude, but it doesn't have a direction really. Okay. So there's another, I didn't put the word up there. Oh, sorry, I meant to show you one more thing. Okay, so that vector means 3 meters per second. What do you think this vector means? If I'm saying that it's also a velocity, what does it mean? I tried to make them double the length, so what do you think? How about 6 meters per second, right? The size of a vector reflects how big it is, right? The magnitude means the size of it. So how fast you're moving, maybe, right? That would be the magnitude of the vector. But it could have been a force, right? And everybody remember the units of force? They're called newtons, right? So this would be a force vector, and this would be a 6 Newton force vector, twice the magnitude, because it's twice as big, okay? So you have magnitude, you have direction, which means size, and of course direction. Okay, so vector. Newton's laws of motion. First law of motion. An object at rest stays at rest. An object that is moving will keep moving in a straight line, which means with a constant velocity, unless what? Acted upon by an outside force. It's got to be an outside force. Internal forces cannot change the property of the mass, right? It has to be an outside force. Okay, second law. It's an equation. F equals ma, right? And then we rewrote it. A equals F divided by m. Okay, so from that equation, what do you get? Number one, the acceleration of an object is directly proportional to the amount of force you put on it, right? More force, more acceleration. But it's inversely proportional to the mass that you're trying to move. So more mass means what? Harder to accelerate, the acceleration is smaller, okay? And then the second important thing, mass doesn't have direction, but force and acceleration do. Which direction does the acceleration have to be? The same or opposite or whatever direction as the force? Which one? It's got to be the same, right? Force pushes this way, acceleration is this way. Force is this way, acceleration is this way, right? They always agree with each other. This way, whatever, you know, right? Have to be the same. Okay, that's the key thing actually from that. All right. Newton's universal law of gravity. We covered that today. Oy. Okay, it has a formula, big G, big M, little m, M1, M2 over the distance squared. Okay, so we did cover this today. Anybody want a quick review? The key thing was, what about the concept of center of mass? Who knows what that means? What is the center of mass idea? A mathematical location for a mass, right? Where is it located? So where's the Earth located? At the core, right? So when we say, where are we compared to the Earth, we're pretty far away. We're 6,400 kilometers from the Earth right now, okay? And so what happens the further away you get, the weaker the gravitational force becomes. And it's called an inverse square law. So if you go twice as far away, the weight is, or the force of gravity is 1/4 as big. If you went 4 times the distance, 4 times as far, then it would be 1/16 as big, right? 4 squared. So that's why it's called the inverse square law. What is weight? Your weight is the actual force of gravity pulling on you. That is what weight is, okay? Force of gravity. We call it weight, but it is the attraction the Earth has for us, okay? That's what we feel. Centripetal force, when we see things going in a circle, in order to turn, you need to keep turning it. You need a force which is not forward or backwards, it's to the side. And that force has to point toward the center of the circle. So if you're going this way and you want to go around, the force has to push you or pull you to make you turn towards the center of the circle. So that direction is always toward the center. That's actually what the word centripetal means. So if there's a force, it causes an acceleration. How do I know that an object moving, an object is going around, let's say the Earth in orbit, at a constant speed? Is the velocity constant? Constant speed. Is the velocity constant? No. Why not? Because it's turning, right? It's changing direction. So it's constantly changing, right? It's accelerating because as it turns, it's changing the velocity vector's direction. So in order to turn, you need a force. And in order to force, you need, when you push with a force or pull with a force, there is an acceleration that you get. Okay, we talked about this concept today, the escape velocity. What does that mean? So there's 2 kinds of energy. We talked about gravitational potential energy and kinetic energy. And when you try to get away from the Earth, you gain potential energy by losing kinetic energy. You slow down as you get away. And to get away from the Earth or from any body, you have to have a big enough velocity. You have to actually have a big enough kinetic energy. And so that's the escape velocity, the speed needed to get away from a body. And for the Earth, it happens to be something, the moon is a lot easier, Mars is easier. Okay, there's a lot of easier things. Okay, be able to, jumping down here, be able to explain why Copernicus's heliocentric model could explain retrograde motion and why it was superior to the Ptolemaic geocentric model. So how did Copernicus explain retrograde motion? You remember, yeah. Super simple idea. The planets travel at different speeds. Which one travels faster, the closer or the further ones? The closer they are, the faster they go, right? The closer they are, the faster they go. Mercury is the fastest planet in our solar system. Venus next, Earth is third. And what happens is one planet passes another, and it looks like it's going backwards. Okay? It's the appearance of going backwards, retrograde motion. So why is this superior? Because it is much simpler. If you remember the concept of Occam's razor, it doesn't require a lot of parts. The theory is very simple. And it works perfectly, does it? Okay, you're actually supposed to know this. Does it work perfectly? Copernican model worked perfectly. Not really. It actually wasn't very good. And do you remember the one big flaw, the major flaw that it had? Perfect circles, right? And it took Kepler to come and say, wait a second, it's not a circle, it's supposed to be an ellipse, right? If you turn it to ellipse, it suddenly becomes really amazing. That it absolutely is fantastic and powerful. Okay, so I'm going too slow. There we go. What is the significance of Tycho Brahe's contribution? What did he do? Tycho Brahe, what's he known for? His beautiful astrolabe, right? The ability to measure the positions of the stars and planets. He collected data for over 25 years. And who finally analyzed the data, figured it out? Johannes Kepler, right? So Tycho collected the data. He was the great observer and spent his whole life collecting data, but it was really Johannes Kepler who figured it out and made the laws of planetary motion. Okay, so use this. We just did. We did that. Describe the major discoveries of Galileo. Okay, so I already mentioned a bunch of them. Features on the moon. What does this tell us? The moon has features. It's not perfect, right? It's not just a smooth, perfect sphere. It has mountains and weird features, right? Craters and things like that. It's rough and smooth in places. It's interesting, but that contradicted, that's what I want to say. Contradicted the original Greek idea that the heavens were perfect. Okay, thank you. Contradicted. Okay, and then what else? How about this sunspots, right? He saw sunspots. That was, again, a flaw in something that was supposed to be perfect. And then he saw the phases of Venus, the stars of the Milky Way, and of course, the moons of Jupiter, right? They orbited clearly not orbiting the Earth. They orbited Jupiter. And again, that was supported by the Copernican theory. Okay. Okay. How did Galileo? Okay, sorry. Keep going. Oh, I did that. All right. Describe Galileo's discovery about mass and acceleration. You remember what it was? All objects, regardless of their mass, fall with the same acceleration. Back in the Greek times, Aristotle said, heavier objects fall faster, right? So there's, yeah, he's wrong, right? What he misunderstood is that the air gets in the way. There's other things that are in the way. So that's just not right. Describe how fast force causes a mass to accelerate. We kind of did that. But let's go back and do the two other cases, right? If you push in the same direction that you're already moving, what will happen to you? You will speed up. If you go push backwards from the direction you're moving, you will slow down. And then to the side, you'll turn. Okay, those are the only three options, really. Okay. Blah, blah, blah. Oh, yeah, I did that already. Okay, calculate the difference in the strength of force of gravity. I feel like we did that a couple times already. Are you okay? Force of gravity. Further away you go, the weaker it gets, 1 over r squared. Describe how planetary mass and radius affect the escape velocity. Ooh, I didn't really talk about this. Would you like to try? See if we can figure this out. So we take a planet. We want to get away from it. Okay? What happens if the mass of the planet gets bigger, but the radius stays the same? It becomes more dense, right? Would it be easier or harder to get away? And explain why. Harder? Okay, why? Why is it harder to get away? More mass equals a stronger force of gravity, right? Does that make sense? So it's harder to get away. What if there was less mass, same radius? Same argument. Less gravity means it's easier to get away, right? But what if it's a smaller mass and a smaller radius? That's a little harder to say. Actually, we're not really equipped to say that one, so I shouldn't even have asked you. But it turns out it is easier to get away from the moon because it's a lot smaller mass, but not quite as much smaller on the radius. Okay, so yeah, there's a formula. If you want to figure this out with real formulas, take the astrophysics class in the fall. We do that. Okay, yeah, actually, it's so easy. I could derive it with you in like 2 minutes. Want to do it? Just kidding. You want to come to my office? I'll show you. It's really fun. All right. Let's see, the order of the planets in the solar system. Starting at the center, we got the sun, the first planet. Mercury, second planet. Venus, third planet. Earth, fourth. Mars, next one. Jupiter, Saturn, Uranus, Neptune. Excellent, okay. Kepler's laws of motion, Galilean moons, Newton's laws of motion. We got that, okay? Chapter 2, we jumping? 2 or 1? 2? 2, okay. 2. Okay, chapter 2. You may find this a little bit easier, I hope. Earth rotation. What's going on? Earth is rotating. Okay, there's an axis of rotation. And actually, let me go ahead and bring it up right now because it's a number you need. How is the axis of the Earth tilted? 23.5 degrees. You got to memorize that number. Okay, so there's a rotation. And how long does this rotation process take? One period is a day, 24 hours. Okay, that's good enough. And then we have Earth revolution. What does it refer to? The movement around the sun. We revolve and orbit around the sun. How long does that take? What's the period of revolution? 1 year, 365 days. So we got period of rotation, period of revolution. It's just the time it takes, right? The horizon. What's the horizon? The boundary between the sky and the Earth, right? It's the line between the skies. Okay, and altitude refers to the angle above the horizon, altitude. So in particular, the altitude of the North Star, for example, right? One of the things that they noticed a long time ago is that Polaris, the North Star, is not always in the same altitude, right? It's affected by where you are on Earth. In fact, really cool, if you were to stand at the North Pole, where would it be? It'd be right above your head, okay? It's clearly not above my head now. It's over there in the north, right? It's actually, by the way, 34 degrees above the horizon. And Santa Barbara is at a latitude of 34 degrees north. Do you see a connection? Okay, so what happens as you go further north? Polaris rises in the sky. If you go as far north as you can, North Pole, what's the latitude? 90 degrees north, then it's right above your head, and that happens to be an altitude of 90 degrees. Okay, so that's the connection. Latitude and longitude. Latitude is a measurement of what? Where are you going on the Earth? You're going above or below the equator, right? And longitude is measured along the equator. Okay. So which one changes the altitude of Polaris? The latitude, right? That's the one that changes. If you go along the equator, nothing happens to Polaris. It stays in the same place. Angular size. Okay, this is an idea that if you look up, for example, we held up our pinky at arm's length. Anybody remember the angular size? 0.5 degrees, okay? And so this should be able to cover up the moon, and don't do it, but you could cover up the sun with safety glasses, which I will give you at some point. There are glasses that let you look at the sun. Okay, I'll give you some of those pretty soon. But anyways, you could cover it up because the angular size, the angle that an object makes is what we measure in astronomy. And the angular size of the sun and the moon are both about 0.5 degrees, which is why eclipses are possible. Question? Question? Wait, a little louder, sorry. Oh, sure. So latitude, okay, let's do longitude first. Longitude is measured along the equator. Longitude, along the equator, right? And it starts at one particular place called the prime meridian, where it crosses the equator. That's 0 degrees longitude. And you can go either to the east or to the west, but longitude is basically a measurement around the equator. Latitude is a measurement above or below the equator. So you make a circle around the Earth, which is parallel to the equator. As you go up, the circles get smaller, by the way, right? Because the Earth is getting a little bit smaller. And at the point at the top, you're at the North Pole. But that circle that's parallel to the equator is the same latitude anywhere you go around that circle. It's the angle above the equator. That's a north latitude. So you make a little circle below the equator. That would be the latitude as well. So it's the angle measured along the surface of the Earth to the north or to the south. We call that the latitude. So it goes from the equator, 0, to the North Pole, 90 degrees. Okay, so you follow a meridian line. I think don't worry too much about that. It's just a little thing. Okay, celestial sphere. What's a celestial sphere? The stars around us, right? If we make an imaginary sphere around us that's perfectly centered on the Earth, so we have a North Pole, you go straight up, you hit the celestial North Pole or the North Celestial Pole. If you go down to the bottom of the Earth, you get to the South Pole, go straight away from that, you hit the South Celestial Pole. If you have an equator for the Earth, you go out, you hit the celestial equator. That like mimics exactly what the Earth is doing. But the Earth is rotating towards the east, right? Which way do we see the stars moving? Towards the west. Are the stars moving? No, it's us, right? We're the ones rotating, but we see the stars moving because of our motion. Okay, that's relative motion. All right, okay, so celestial equator, North Celestial Pole, South Celestial Pole. These are on the celestial sphere, okay? Polaris, the North Star, zenith. Okay, Polaris, do I need to explain that? The star that the axis of the Earth is pointing at right now, okay? That's it, special, because it doesn't move, right? The stars rotate around it, but it doesn't move. Zenith is the name that we give the point right above our head, wherever we are, right above our head. Meridian, in the air, you know, we're out underneath the stars. If you take a line that goes from the north point on the horizon through the zenith. That's why we need the word zenith. Over to the south part of the sky. It cuts the sky into an east half and a west half. And when the sun is crossing this meridian line, what time is it? It's noon, right? That's the definition of noon. Okay, declination is, okay, so actually I should go back because it looks like I left off the word right ascension. Why did I do that? Okay, the celestial sphere has measurements in the same way that the Earth has measurements. So let's go back to your question if I could. We had longitude, which is measuring around the equator of the Earth. On the celestial sphere, when you measure around the equator, we call it the right ascension, RA, right ascension. And it's measured from 0 to 24, right? Why? 24 hours in a day. That's why. So it goes from 0 to 24 hours of right ascension. And then if you imagine how latitude works, you go up or down, above and below the equator. The same thing on the celestial sphere is called declination. So if you go above the celestial sphere equator, celestial equator is called positive declination. Below the celestial equator is called negative declination. If you remember, the reason we're learning about this is that we talk about the path that the sun takes through the sky. And it turns out that the sun rises in the east exactly and sets in the west exactly on 2 days per year. Does anybody know the names of those 2 days? You're all supposed to know. The equinox is the answer, good. But they're the vernal equinox and the autumnal equinox. And the reason why is the sun is crossing the celestial equator on those days. On the vernal equinox, it's going up, and after the vernal equinox, the sun is going to be above the celestial equator. And then on the autumnal equinox, it's passing back down, and after this, it's going to be underneath the celestial equator. And so as a result, the days are longer between the vernal equinox and the autumnal equinox, and the days are shorter in the period between those two the other way, right? So, and when it's below the celestial equator. So when the sun has a positive declination, it's above the celestial equator, and below the celestial equator is called a negative declination. Okay, sidereal day and synodic day. Oh man, did we talk about this for real? Okay, oh I did. Okay, so what do you remember? Okay, I did, I talked about this. Yeah, what's a sidereal day? Okay, so one full rotation, 360-degree rotation of the Earth. So that's relative to the stars, okay? A synodic day, which is what we call a day, is the one that's related to the sun, okay? So from noon to noon, which by the way is the definition of 24 hours, okay? That's how we define a day, okay? But the problem is that in one day, does the Earth stand still? The Earth does not stand still. In one day, it moves a little bit in its revolution around the sun. And so the answer to the question, why aren't they the same, is, should I draw the diagram real quick, or do you guys remember, or do you want to do it? Who wants to see it again? Anybody? Anybody, one person? Everybody's good? Everybody understands it, huh? You got it? Okay. I'm not going to draw it again. Sorry, people at home. They understand it. Hopefully you do too. Okay, so it's actually a difference of 1 degree. So 360-degree rotation, the stars come back. But 361 degrees is about how much the Earth has to rotate for the sun to come back. And that takes an extra 4 minutes or so. So there's a little tiny difference between these two definitions. So sidereal, relative to the stars. Synodic, relative to the sun. Okay, so if you see those words again, that's what it's all about. Okay, it means we're using the sun or the stars to keep track. Okay, small angle formula, wow, I put it in there. It's just not a big deal, but it's really not in your class. I just threw it in there. Okay, it says that you can calculate the size, angular size of something based on how far away it is, right? So something has an angular size. The further away you go, further away it is, the smaller it becomes. That's it. That's all you need to know. Stop. Skip. Not important. Okay, vernal equinox, we talked about this. What date is the vernal equinox in the northern hemisphere? 3/21. In the southern hemisphere? Ooh, you got to think about it. 9/21. So the vernal equinox is the spring, right? The day of spring. And it changes, it flips for the southern hemisphere. It's the opposite. Don't forget that. You need to know that. There is a question about southern hemisphere, okay? Just because I just want you to think about it. It's just opposite, okay? Opposite. So what's the date in the northern hemisphere for the summer solstice? 6/21. It's coming up in our class. We're going to actually pass right through the summer solstice, the longest day of the year, shortest night. Vernal equinox, how many hours of sunshine? 12 and 12. 12 hours of sun, 12 hours of night. Autumnal equinox, same thing. 9/21 for northern hemisphere, 12 hours. The longest day, and the winter is the shortest day. The length of day and night changes depending on what your latitude is, but it will always be 12 and 12 for any latitude on the equinox. Okay, orbital period, I think I mentioned that already, right? Orbital period. Ellipse, okay, we talked about ellipses already. Precession of the Earth axis, okay. This is a tiny little detail, but something important. The Earth has not always pointed at Polaris, and it turns out will not always point at Polaris. There's like a top, gently changing direction, just a little bit at a time. The whole process of changing takes 26,000 years. So in 10,000 years, Polaris will not be the North Star. But in 26,000 years, it'll come back again, and it will be the North Star again. So it's a very slow process called the precession of the Earth axis. Very, very long period, okay? What's a constellation? Constellation? A group of stars that are close in the sky, okay? They've been grouped together by us humans. It's like looking at clouds and seeing pictures, okay? That's what, it's just imagination. But there are certain, okay, the ecliptic, what's the word ecliptic? Has multiple meanings. One meaning in this case maybe would be the path that the sun takes through the sky. The path through the constellation, sorry. The path that the sun takes through the constellation. Another definition is the ecliptic plane, right? Which is the plane where all the planets and the sun are orbiting together, the ecliptic plane. So zodiac constellations are, why are they special? They are the ones that the sun passes through, okay? The phases of the moon, woo, okay. Do I need to review? How much do I need to do? No. Phases. The phases are new, waxing crescent, first quarter, waxing gibbous, full, waning gibbous, third quarter, waning crescent, and back to new. Okay, but you're supposed to know when they rise, when they set, right? Things like that. Actually, here's a question. I hope you'll get this. Which planets are sometimes confused, or are called, rather, they are called morning stars or evening stars? Which two planets are called morning stars or evening stars? Remember what they're called? Mercury and Venus. If you didn't remember that, this is something kind of cute. But the reason is that they're closer to the sun. So as a result, we always see them near the sun, right? So if it's a morning star, what does it mean? When do you see it? In the morning, before the sun rises, right? So it's just a little bit above the sun, never very far. You never see Mercury or Venus far away from the sun. You never see them in the middle of the night. You cannot. They're too close to the sun. So you always see them when the sun is nearby. So just before the sun comes up, they're morning stars. And if they're behind the sun, just after the sun sets, they're called evening stars, right? Get it? Because they're closer to the sun than we are, we never see them far away. What phase can Mercury and Venus be? They can be all phases. But what about the other planets, the ones that are further away? They will pretty much always be full or nearly full. Synodic month, relative to the sun, how long? It's a number, yeah, 29.5 days, a month, a moon, right? This is the lunar cycle that we know about. But the time it takes the sun to go, the moon, to go once around the Earth is actually less. It's only 27.3 days. That's called the sidereal month. What is the solar eclipse? What's happening? Tell me, describe it. Solar eclipse? The sun is being blocked by the moon. We are in the shadow of the moon, in other words. What phase is the moon? What does it have to be? This question comes up a little bit later down here. Has to be a new moon. Okay, it has to be. And not only does it have to be a new moon, it has to be passing through what we call a node. Remember that? The moon is tilted in its orbit by how many degrees to the ecliptic plane? 5-degree tilt. Not a lot, but it's enough to mean that we don't get eclipses every month. See you guys later. Mañana. Okay, and lunar eclipse happens when? How does it happen? The moon, yeah, the moon is in the shadow of the Earth, right? So what phase is the moon? A full moon. Has to be a full moon, okay? The umbra, penumbra, what does it mean? Umbra? The darkest part of the shadow, right? Dark. No light can get there. Penumbra is partial shadow, and it's really not that interesting. So if you see a penumbral lunar eclipse, it's totally not worth it. Well, I mean, the moon is beautiful, but it's not fun for watching eclipses. The umbral eclipse is the fun one, okay? Totality means what? It's completely in the shadow somehow. Partial means partial, not completely in the shadow. Annular, special word, what does that mean? An annular, that's a solar eclipse. What do you see? See a ring of light. Why? Is the sun too big or the moon too big? Or the moon too small? The moon's too small or the sun's too big? Maybe both. How does that happen? So remember that the sun and moon can change sizes just a little bit. How do you get a small moon? What happens? The moon looks a little small. So the moon's in its orbit. Where is it? The moon's in its orbit at apogee, right? Furthest from the Earth, so it's a little bit smaller than usual. And now the Earth goes around the sun. How do you get a big sun? The Earth is near perihelion, right? And so if those two factors come together, you can't block the sun anymore. You get an annular eclipse. Okay, penumbral eclipse, boring. Perigee, what's perigee? Closest to the Earth, right? G, perihelion, closest to the sun. Okay. Okay, apogee, farthest from the Earth. Aphelion, perihelion. Okay, nodes, retrograde motion. Nodes, what's a node? The moon passes through the ecliptic plane how many times per month? 2 times. One's going down, one's going back up. Okay, 2 times. And then retrograde motion, when we see a planet. So normally planets have prograde motion. There's the word. What direction do they move through the constellations? Normally, towards the east, through the constellations, right? What's retrograde motion? When they temporarily move backwards, and then they go back to being forward again. Okay, retrograde motion. How many planets, which of the planets will undergo retrograde motion? All of them is the right answer, okay? That's different time. Geocentric means what? Geo, Earth is at the center of the solar system or the universe. And heliocentric, the sun is at the center. That's the right one, right? Stellar parallax, Aristotle did not see it. What does stellar parallax mean? Stellar meaning star. Parallax meaning a shift, right? So we use the example of our thumb, right? If you use different eyes, your thumb appears to shift slightly compared to the background. Aristotle said, I don't see that happening. If the Earth is moving, then the stars should appear to move. But in fact, are they moving a little bit? Too small for him to measure. We now have the technology, but back then you didn't have it. So stellar parallax, we know the idea, right? The stars should move if the Earth is moving. And in fact, we now have that capability of seeing that. Deferent, which model are we talking about when referring to the deferent? The Ptolemaic model. The deferent was the main circle that the planets followed. Remember, Earth is at the center. The moon goes around it, and then everybody else goes around on a deferent. And many of the planets, not the sun, have an epicycle on top of it. And the epicycle is supposed to explain retrograde motion. That was his way. Why does it do that? He had no idea. He was just trying to build a model. Okay, Occam's razor one more time. Given a choice, simple or complicated is the preference. Simple theories which can explain the evidence are preferred over complicated theories that explain the evidence. We go for simple. Okay, describe the reason for seasonal changes. Whoa! Okay, the reason for seasons is because the Earth is in an elliptical path, right? The Earth is in ellipse, right? When do we have our summer? When we're closest to the sun, right? No. Remember that that's not right. Right? When are we closest to the sun? What month? January. Ooh, that's supposed to be cold. Okay, why do we have seasons? Tilt of the Earth. Okay, now give me the 2 reasons. There's 2 reasons for seasons. Give me one. No, I'm sorry. Give me what happens as a result of the tilt of the Earth. Okay, it's all about the sun. Give me the sun. Sunlight. Okay, so the sun, what is it? Okay, so right, so we're facing the sun is higher in the sky, the light comes down and is more intense. The light is more intense. What about the length of the days? They're also longer, right? So longer days, more intense sunlight, summertime. Wintertime, the sunlight is less intense, it's more spread out, less intense, and the days are shorter, it's cooler weather, okay? Determine the rising time. Rising time, do you want to practice? Here we go. What time does a first quarter moon rise? What time does a first quarter moon rise? What time? I didn't hear you. 12 noon? Did you look at your notes or did you just figure it out? Okay, the way I remember it is, a first quarter moon is right above me when I'm standing between light and dark, which happens to be 6 p.m., right? Sunset. The sun, it'll be right above me. So it's highest at 6 p.m., which means you're right. It rose at 12 noon. It's going to set at what time? At midnight. So when will it be in the west? The western horizon? At midnight. When will it be on the eastern horizon? At noon, right? So the time that it's on the western is when it's setting. The time that it's on the eastern is when it's rising, right? You got those 2 things, okay? Crossing the middle meridian line, okay. Describe the geometry of an ellipse. How do you get an ellipse? Eclipse, sorry, not an ellipse, eclipse. How do you get an eclipse? When the sun, moon, earth, or sun, earth, moon are all in a line, right? They're perfectly aligned. It happens every month, right? Happens every month? No. Remember, it doesn't happen every month. It would if the moon was in the same plane as the earth. But it's tilted by how many degrees? 5 degrees. And so you not only have to have the right phase, but it's got to actually be in the ecliptic plane. It's got to be perfect. And that only happens once every 6 months or so. Although you can have 2 back-to-back. You can have a solar, then a lunar, or lunar, then solar in a very quick little time because we have these eclipse seasons, right? So 2 weeks apart, you can have that. How do you get the longest solar eclipse? Long solar eclipse. You want a big moon or a small moon? You want a big moon. You want a big sun or a small sun? Small sun, okay? That way the moon can block the sun for a long period of time, okay? How do you get a big moon? The moon goes around us, where would it be? Big moon. At perigee. Perigee, closest to the Earth. How do you get a small sun? The Earth goes around the sun. How do we make it look small? We're at aphelion, okay? That's the longest possible eclipse, and it's 7.5 minutes or so. You can't get any longer than that. That is the longest, okay? I just talked about Aristotle, right? Why did he believe geocentric? There was no stellar parallax. Geocentric, I think I got that, okay? Different epicycle to describe retrograde motion. Okay, memorize. Okay, angular size of the sun and the moon is about 0.5 degrees. The dates of the equinoxes, the tilt of the Earth, the precession of the Earth axis, 26,000 years, phases of the moon, sidereal, 27.3, synodic, 29.5. Ooh, the days of the week. Let's do that together. Sunday, what day is that? The day of the sun, Sunday. Okay, that was easy. Okay, the next one. Moon day, right? Of course, okay? The next one. Martes, Mars day. Actually, any Latin language will work, right? So, lunes, martes. What's the next one? Miércoles. Which day is Wednesday? Wednesday is Mercury day. That's what we should say. Today is Mercury day, right? That's why we're studying for the test on Mercury day. Never mind. Okay, tomorrow is Jueves, Jove, which is Jupiter Day. Okay, you have to memorize that one because Jove is not what we usually call it. And then Friday, Viernes, Venus Day, and go back to English, Saturn Day. Okay, you got it? Okay, 7 days of the week, 7 important hours. You want to do one more? I'll keep going if you want. Want to do one, or you're done? If you're done, just go. It's fine. You don't feel rude. But if you want to keep going, anybody want to keep going? One person wants to. Okay, let's do it. Chapter 1. You can leave though. If you want to leave, leave. Okay, chapter 1. What the heck? Just like to finish. Okay. Oh, it's not even that long. Okay, here we go. Now it's the easy one. Okay, kind of. Scientific notation. Okay, so you need to know how to write a number in scientific notation or transform it from scientific notation into normal notation. Anybody want to practice? Practice? Okay, let's do a quick practice. We'll do one of each, okay? So I want you to convert a number into scientific notation and then take a number out of scientific notation into normal notation. Thank you, guys. We'll see you tomorrow. Okay, so here we go. Take a number. Let's do this number. This is my, I don't know. Okay, let's do 1,703. Let's call that meters. I don't know, 1703. Can you write that number in scientific notation? So if you look at this number, if you need any help, you want to remember that if you can't see a decimal point, where is it? It's here at the end of the number, okay? And you're going to move it in order to get a number between 1 and 10. So I'm going to move it which way? Well, if I move it this way, it's getting smaller, so that's a good thing. And I move it again, and I move it 3 times altogether. So now I have the first part of my number. 1.703 times, and then you count how many times you had to move the place. So what would I write? 10 to the 3rd power. That's the scientific notation. Okay, should we try to go backwards? Let's go backwards. Let's give you a scientific notation number. Let's do 3.17 times 10 to the minus 4 seconds. I don't know, whatever. Okay, so what does the negative mean? It's a small quantity. You're going to move the decimal place the other way. How many places? 4 places. So I'm going to go like this. 1, 2, 3, 4. And that's where the new decimal place is. I need to fill in zeros to give me the right answer. So the answer is 0.000317 seconds. Okay. Try one more. Let's do one more. 5.67 times 10 to the 8 kilometers. Okay. Hey, what would that be? Hey, yeah, you're gonna go this way. 5. Okay, so you're gonna go 1, 2, 3, 4, 5, 6, 7. Oh, that's a lot of zeros. I'm gonna add on all the zeros. Okay, so that's 3, 6. Anybody tell me that number in words? 567 million kilometers. Okay, all right. So you would recognize the answer, right? Everybody good? Can you do that? Okay. So that's 567 million. Okay. All right. Can you guys see that at home? Here are my examples. Okay. Very good. Okay. Nobody's actually watching. No, no one's even watching. It's all right. I got 3. No, I did have. Oh, I got 3 people. Hey, 3 of you. How you doing? Okay. Oh, let's keep working. Okay. Order of magnitude. Order of magnitude is the closest power of 10. The easiest thing to do is write the number in scientific notation. Let's just take all these numbers and quickly get their orders of magnitude. Okay? Like this number right here. What's the order of magnitude? Yeah, it's 10 to the 3rd. Okay, I like it like this. I know the author just does the power. That's not really right. I'd go with this. 10 to the 3rd power is the order of magnitude. Okay. How about this number, 3.17 times 10 to the minus 4, order of magnitude, 10 to the minus 4, right? So what happened? We just ignored this first part because it was less than 5. But here we have an example. 5.67 times 10 to the 8th. Now this is bigger than 5. What do? You bump it up. So what's the order of magnitude? 10 to the 9th. Okay, make it go up by 1. The hardest thing that people have trouble with is what about 9.1 times 10 to the minus 3? Okay, what do you do with that? So this is 9.1, it's bigger than 5. What happens to the power? It goes up by 1. So what do you get? 10 to the negative 2. Just remember that because it's negative, you're actually going to make it go up by 1, which makes it negative 2, not negative 4. The most common mistake is negative 4, right? People get confused by that. All right, what is a planet? Okay, so again, you don't have to memorize sizes, but if I gave you the sizes as an example, you would be able to deal with the information and talk about how much bigger or smaller. So in the course, we talked about the average planet size. It's about 10 to the 6th kilometers. 10 to the 6th kilometers. And is that right? No, that's not right. 10 to the 6 meters, sorry. 10 to the 6 meters. A star is about 10 to the 9th meters. How much bigger is a star than a planet? So it's 3 orders of magnitude, like 1,000 times as big. Now, our planet is a little bit bigger than usual, and our star is not a lot bigger than usual. So it turns out our planet is actually, it would only take 109 Earths to cross the sun, which would mean that you could fit 1 million of them inside of the sun. But anyway, that's kind of amazing. All right, so, okay, so what's the smallest thing? The planet is kind of the smallest body that we talk about. The next would be star. And then the next comes a solar system, right? A solar system is larger than an individual star. It was like 10 to the 12th, right? 10 to the 12th, the size of a solar system. A galaxy is much bigger than that. It's like 10 to the 21st, okay? So again, these are just numbers, 10 to the 21st meters. And then bigger than a galaxy is a cluster of galaxies, 10 to the 23rd, right? And then we have a supercluster, 10 to the 24th, right? So if I give you these different powers, be able to describe how much bigger or smaller they are. That's the kind of idea. And know which one's bigger. What is a galaxy, for example? Oh, well, okay, what's a planetary system, solar system? What is that? How do you describe it? What is it? You got a star, a sun, right? And then you've got stuff around it. Planets, stuff, comets, asteroids, whatever, all that junk around it. Okay, that's a solar system. What is a galaxy? Collection of a bunch of stars, right? How many stars? Like billions of stars. Each galaxy has billions of suns in it. Billions. Our galaxy has 400 billion stars in it. Okay. What is a galaxy cluster? It is a group of galaxies that are together. Okay, and then you have groups of groups, which we call a supercluster. So we be able to talk about which one's bigger, right? Or arrange them in order of their size, right? Which one goes first, right? So a solar system is obviously bigger than a star, right? And a planet is smaller than a star. A galaxy cluster, how is that compared to a solar system? Well, it's much bigger, right? It's huge. Okay. All right. Supercluster, universe. What's the universe? Big. Actually, it's kind of like, what is the universe? That's part of what we're going to try to do with, deal with in our course. And really, it's kind of at the very end, we're going to hit some of the most important ideas in that. But the universe is everything, right? What we can see and even what we can't see yet. There's an astronomical unit. You need to know what that is. Who knows what an astronomical unit is? Average distance from the Earth to the sun. Okay, that's a number. That's a number. You don't have to necessarily know the number, but you need to know what it is. Okay, a light year is what? A light year. How far light travels in a year? Good, good, good. And so the idea is that when we look at stars that are very far away from us, the light has been traveling for a while to get to us. So we're looking back in time, right? The further away they are, the further back in time we're looking. So if I look at a star that is 50 light years away, the light that I'm seeing left the star how long ago? 50 years ago. And it's been traveling to me for 50 years. Finally, I'm seeing it, right? So I'm not seeing it as it is now. I'm seeing it as it was 50 years ago. What about stars that are 1 billion light years away? Same idea. We're looking at, or galaxies, right? We're looking at the light that came 1 billion years ago and is finally getting to us now. Okay. So I realized something important. You guys stayed to the end. Thank you, because I actually have something important you need to know. You need to know roughly how old the Earth or our solar system is, and roughly how old the universe is. You need to know that. There's a question that you're going to need to answer. Does anybody know how old the Earth and the Sun is? They're about the same. About 5 billion, yeah, 4.6, but let's say 5 billion years old. Okay, the Sun and the planets around it are about 5 billion years old. But we think that the universe, and we might be wrong, but it's still the best answer that we have. We think that the entire universe is about 13.3 billion years old. So again, friendly, it's about 15, and the sun and our Earth is about 5. So how old is the Earth compared to the universe? So it's about 5 compared to 15, about 1/3 the age, right? So was our Earth and our sun born at the beginning of the universe? No, because it's been around like 15 billion years, and our sun has only been around 5 billion years. Okay, so a lot less time. Okay, what is a parsec? It's a distance in astronomy, and we'll learn more about it later, but it's exactly 3.26 light years, about 3 light years. It's good enough for now. Okay, change between ordinary scientific number, we did that. Determine the order of magnitude, we did that. Add, subtract, multiply, and divide. Oh, I didn't do that. Do I want to do that? You guys want to practice? Anybody? Practice? It won't be very hard, but you might have 1 or 2. Practice? Anybody? Practice, practice, practice. Don't be shy. We'll do that? Okay. So maybe I'll just skip down. Let me come back and do that in a second, okay? Organize items by size, okay? Subatomic particle, atom, dust, single-celled organism. Describe the steps of the scientific method. Oh, I think I've left out a bunch of stuff. I think I did, right? Because where are all the terms? Oh, there we go. Okay, I left out some stuff. Let me make sure I finish that. The scientific method, what is that? It's a method for building knowledge, okay? So it begins with, can you remember the ideas? How do you begin? Make an observation. Look at the world. Find something that you're curious about. Then learn as much as you can, and then begin your science. What do? Make a hypothesis. How do you think it works? So the hypothesis is not random and based on no information. It's based on the best information you have. So a scientific hypothesis, in order to be scientific, must be testable. So after your hypothesis, what do? Perform an experiment, okay? The experiment comes out and it either supports you or refutes you, right? One way or the other. It doesn't matter. It's all good science, right? You learn something. So what happens if you're successful? Well, you say, good for me. That's great. That must have worked. But you might try it again with a little bit further constraints, maybe to try to do it even better, a more precise hypothesis. Try it again. And you keep trying, by the way, until you fail so that you can learn something. Failure is a way of learning, right? New information. It's not a bad thing necessarily. Anyways, if you do have a failure, you're going to have to take the information you just learned and incorporate it into a new hypothesis and try again. So you just keep going and you build. And it's a method of building. What's a hypothesis? Your best guess. A theory. A theory is powerful, right? When we learn the theory of relativity, the idea is to understand that it has been tested over and over and over again, and it still works beautifully. We feel incredibly confident that it will continue to work in the near future, okay? So a theory is a very respectful way to say this idea is worthy of your respect and belief, okay? And you should test it, but you will probably find it works, okay? So it's not just a theory. If you hear people say something like that, there's the idea that, oh, it's just a theory. No, that's not the way it works. A theory is an incredibly tested over and over again. We feel very confident that it is incredibly close to, I don't want to say truth, but it's closer to the truth than anything else we have, okay? Pseudoscience means false science. And what does it mean? It might make predictions, right? So no, it doesn't say astrology. It could, yeah, probably astrology. But pseudoscience is the idea that it makes predictions, but if you really test them, they don't really work. It has to be done in a particular way. And that's not science, okay? It can't be one person sees the truth. It's got to be something accessible to anyone. Okay, and I will do a couple of examples of the scientific notation add, subtracting, but let me just quickly jump through here because we're almost done. So testable is the main thing. Okay, memorize the size of the Earth. The radius is 6,400 kilometers, 4,000 miles, which means the diameter twice as big, 12,800 kilometers, 8,000 miles. The moon is 1/4 the size of the Earth. So how many miles would that be? 2,000 miles across or 1,000 miles in radius, okay? And you could do the other one as well, 1,600 kilometers radius or 3,200 kilometers diameter. Oh, I just said that, okay? The sun is about 100 times bigger than the Earth, not 1,000, okay? Because our Earth is a little bit bigger than the typical star. Okay, so now I want to do a couple of examples of add, subtract, multiply, divide, and then we're done, okay? So good job, you guys. You're going to be ready, I hope, tomorrow. Come in, it's a lot of stuff, I know. You can do it. Get a good night's rest. It's more important than studying until the wee hours of the night. Okay, let's go ahead and do some multiplication division. They're easier, right? So multiply. Okay, 4 times 10 to the second times 6 times 10 to the third. Okay, I'm just trying to throw out a couple of examples. The cool thing about scientific notation is you break it into the pieces, right? You do 4 times 6. 4 times 6, 24, okay? And then you take the powers of 10 and you multiply those together. And what happens when you multiply powers of 10? You add the powers together. So it becomes 24 times 10 to the 5th, right? Okay, is that an answer right there? Look good? Okay, what's wrong with the first piece here? It's not between 1 and 10. So don't forget, to fit the scientific notation format, you've got to make the first number between 1 and 10. So what's 24? If I move it 1 decimal place, now it's going to be between 1 and 10. So this is 2.4 times 10 to the first. That's what this is. And then times 10 to the 5th. So in other words, what do you get? This is 2.4 times 10 to the 6th. That's the correct scientific notation. Okay, you got it? Cool. Okay, division, even easier. Actually, it is easier, really. Let's try. Okay, let's try 8 times 10 to the 7th divided by. Can I just keep it easy, or you want to make it hard? 2 times 10 to the 3rd. Okay, dividing. Keep it easy, okay? So you do the parts separately. 8 divided by 2 is 4, right? You do that part. And then you do 10 to the 7th divided by 10 to the 3rd. This time, you subtract the powers. Oh, 4 times 10 to the 4th. I guess I like 4s today. Okay, 4 times 10 to the 4th. Okay, then the next step, addition, subtraction. It's actually the same problem. If you add powers that are the same, it's super easy. But if the powers are different, you have to make them be the same. So just to give you a quick example, let me do one of each. One where they're the same and one where they're different, okay? So, I don't know, 5.1 times 10 to the 3rd plus 1.2 times 10 to the 2nd, 10 to the 3rd. Sorry, I'm trying to keep the powers the same. Okay, so if the powers are the same, then this is the easiest problem ever. You just add the first parts together. That means 6.3, and you keep the same last part, times 10 to the 3rd. Okay, that's the answer. That's the easy one. The harder version is when one of the powers is different. Okay, so I could take the same thing, 5.1 times 10 to the 3rd plus 6 times 10 to the 2nd. Okay, 6 times 10 to the 2nd. Everybody understand? These powers do not match. You can't just add them together. So what I need to do is make the powers the same somehow. And there's 2 ways. I can either lower this one or I can raise this one. Okay, I think raising is easier, so I do that. So how do I make the power go up by 1? Well, every time I move the decimal place, 1 place, it makes the power go up by 1. So instead of 6, I could call it 0.6 times 10 to the third power. Now they have the same power, and I can add these together. And so the answer is 5.7 times 10 to the third. Okay, now I'm going to tell you a real important trick. Because some of this might be hard for you, a really important trick to learn is just rewrite the numbers as ordinary notation, do the addition, and rewrite it back into scientific notation. If you get stuck, don't get stuck. Try to go back to things that are easy, okay? So if I look at this problem right here, what is this number taken out of scientific notation? So it's 5100, 5,100. What's this number? 6 times 10 to the second plus 600. Okay? And so I could do that. I'm pretty sure you're all capable of doing that. 5,700, and that means this is the right answer anyways. Okay? All right, so I'm done. Thank you guys very much. Good job. Give yourselves a hand. Or maybe not. Okay. Thank you at home. We're done with our review. And see you in the morning. We do have time to ask questions in the morning, too.